Recall that electrophilic addition reactions involve the reaction of an alkene with an alkyl with a hydrogen halide to form the more highly substituted alkyl halide by a Markovnikov addition. And so if we have an alkene here plus HBr, we're going to get the Markovnikov addition of HBr across that double bond to give us this alkyl bromide. We say that this is a Markovnikov-like addition, right, because you're getting the substitution, the bromide, attached to the more highly substituted position. This goes through a carbocationic intermediate. Well, this should seem familiar to you. When this reaction was first discovered, conflicting results were reported. In some cases, especially with HBr, the anti-Markovnikov product was generated. We know that this is impossible if the mechanism was truly an electrophilic addition where you have a carbocationic intermediate. Well, it turns out that the quality of the HBr played an important role. While fresh bottles of HBr gave the expected Markovnikov product, older bottles of HBr gave the anti-Markovnikov product. And so it was discovered that old sources of HBr contain a small concentration of peroxides. And we know that since the sigma oxygen-oxygen bond is weak, there is the potential for generating radicals. And so thus the mechanism for the radical HBr addition. And so in the radical HBr addition, we can take this alkene plus HBr in the presence of peroxides, and instead of getting the Markovnikov product, we now get the anti-Markovnikov product. So the mechanism for the radical HBr addition is rather complicated, but we're going to go through it. It can be divided into 4 discrete steps. Many radical reactions are what are known as chain reactions, and so we normally write them stepwise. All right, and so the first step in the radical addition of HBr to an alkene is known as an initiation. And the initiation is really just one of those reactions that we talked about last time, which is the thermolysis reaction. And so we can take, in this case, a peroxide, and we can heat it up, and what will happen is you will generate 2 new radicals. Right? In this case, 2 alkoxy radicals. This then leads us to step 2. So step 2 is what we call another initiation step, but this time it's a different mechanism. This time it's an abstraction. All right, so we first generated this alkoxy radical, OR dot. This alkoxy radical is going to react with HBr, and it's going to give us a new radical. It's going to abstract a hydrogen atom. And so what you're going to get is ROH plus a bromide radical. Now this bromide radical continues along. So step 3 is what is known as propagation. And propagation involves one of those mechanisms that we talked about last time, the addition of the radical to a pi bond. And so we can get bromide radical to react with an alkene. When that happens, the bromide is going to couple to the terminal end of the alkene to give you a new radical up on the secondary carbon. This radical continues along, so step 4 is another propagation step. But this time the propagation step is an abstraction. And so we're going to take that radical, and this time we're going to react it with HBr. This is going to undergo an abstraction step to generate the alkyl halide plus a new bromide radical. Now this is where the chain repeats itself over and over and over again. This bromide radical can recycle. It can go back up to step number 3, and it can undergo an additional propagation step. In order to terminate this reaction, to finish the reaction, we have a step 5. And so this reaction goes between steps 3 and 4 continuously until you've used all of your reagent. And so finally you now have very small amounts of radicals hanging around. And so step 5, you have to quench those radicals. And so this is known as a termination step. And this mechanism is known as a dimerization. And so a dimerization involves two radicals. It doesn't really matter what they are. They're just going to couple together. And so, for example, two bromide radicals could couple together to give you bromine. Let's say you could have this radical coming together with a bromide radical. That's a termination step, a dimerization step. That gives you a different product, this one here. But remember that these products in this termination step, because these radicals are in such small quantities, they're not forming in appreciable amounts. So the major product here is your anti-Markovnikov alkyl bromide. So steps 3 and 4 of this chain reaction are repeated since the bromide radical can be recycled into step 3. And so for the chain reaction to produce the desired product, the propagation step must be more advantageous than the termination step. So in a practical sense, the neutral reagents, the HBr and the alkene, are in high concentrations, and the radical intermediates are in very, very low concentrations. So the chance of having a termination step is actually quite low until most of those starting materials have been consumed. Eventually, those two radicals will combine to form a sigma bond, ending this chain reaction, but this is so insignificant an event that it's really considered inconsequential. So sometimes you might suspect that a reaction operates via a radical mechanism. A quick way of figuring this out is to intercept these intermediates by a radical inhibitor. So what is a radical inhibitor? So a radical inhibitor are reagents that act as artificial terminators. Okay, so one of the examples of an artificial terminator is this molecule here, which is a stable radical known as tempo. Now, if you had tempo in your reaction mixture, if you added tempo to your reaction mixture, tempo is a radical, so what it will do is it will intercept any radical intermediates that are around, and it will undergo a termination step, a false termination step, a dimerization step, so it sequesters any radicals. And so what this does is it then shuts down the reaction and can't proceed. Another type of radical inhibitor are the molecules here BHA and BHT. So these are phenolic, because they have an aromatic alcohol-like functional group. Phenolic-like radicals, because what will happen is any radical that is around will be able to abstract the hydrogen on these two molecules, thereby becoming a new sigma CH bond, and then not necessarily moving on to the next step. Okay? All right, so these molecules here are known as BHA and BHT. Okay, so let's summarize these reactions. So if I were to take this reaction here, this reagent here, I would treat it in the presence of HBr, and then I'm going to have tert-butyl peroxide, diterbutyl peroxide, in this reaction, and I'm going to heat it up. The net result I'm going to get is the anti-Markovnikov addition of the HBr across that formally double bond. Now notice, I used HBr in this reaction. So this is a radical HBr addition. And you might ask yourself, well, why can't we do a radical HCl addition or radical HI addition? It turns out that there are no HCl or HI radical additions. And for that, we need to actually look at the chain mechanisms, because you could probably think about writing a mechanism with HCl or HI. So what we need to do is to look at the thermodynamics of these reactions, because a radical addition reaction will only occur if it's thermodynamically viable. And so let's take a look at the propagation steps in these mechanisms. All right, let's look at that first propagation step. So let's say we're going to add some halide radical to the alkene. Okay, and so if we do that, we get an addition to generate this new radical. Okay, so I'm going to make a table here that has X, where X is chloride, bromide, and iodide here. And I'm going to say what the bond strengths are. So the bond strength for the pi CC bond in each of these cases is 66 kcals per mole. Right, so no change there. What about the bond strength in the products? So in this case, the only difference is we now have a sigma CX bond. All right, so in the case of a carbon-chlorine bond, that's 85 kcals per mole. Carbon-bromine is 72, and carbon-iodine is 57. So what's the delta H for each of these reactions? So we're looking at the starting materials minus the reactants. This delta H is minus 19. This delta H is minus 6. And this delta H is plus 9. Okay? So for the so the overall exothermicity or endothermicity of this step is a combination of the bond strength that you lose and the bond strengths that you gain. So a sigma CC bond has a bond strength of 66, no matter which hydrogen halide is used, but the corresponding sigma CX bond strength depends on the halide. And so what you end up with are two exothermic reactions and one endothermic reaction. Well, this should tell you that the endothermic reaction, plus 9, is not viable for radical addition to alkenes. For the radical HI addition, the first propagation step is substantially endothermic, so the reaction fails. Okay? So we have the possibility, of course, of the chloride reaction still working because it's endothermic for that first propagation step. But let's take a look at the second propagation step. So the second propagation step involves the abstraction of a hydrogen. And so we have this alkyl radical, but now we need to generate an abstraction which is going to take that radical and place a hydrogen there, and then you generate a new radical. So again, I'm going to make a table. Here's chloride, bromide, and iodide. So the bond strength that we have in the starter material is now the sigma HX bond. And so this changes for each of them. So this is 103, 87, and 71 kcals per mole for chloride, bromide, and iodide respectively. If we go over to the products, the bond strength that we care about here is now the new sigma CH bond, and this doesn't change for any of them. So it's still, in this case, 98 kcals per mole. And so if we do starting material minus reactants, we're going to get plus 5, minus 11, and minus 27. Well, we know right off the bat that this reaction doesn't work for iodide because we don't even get there. We haven't even gotten to this step because the first propagation step doesn't work. And so we can see that the bromide works, it's endothermic, but the chloride reaction is plus 5 kcals per mole, and so that's endothermic, and so this reaction doesn't work. So for the radical HCl addition, the second propagation step is substantially endothermic, so the reaction fails. So the next type of reaction that we want to talk about in this section is the free radical halogenation. Besides electrophilic additions and radical additions, another way to make alkyl halides is from the alkanes themselves. Even though we don't think of alkanes as being very reactive, we can still make alkyl halides from alkanes. And the overall reaction scheme is like this. So if you take some alkyl halide, some alkane, and react it with a halogen, we're going to use light to promote this reaction. You're going to replace the RH bond with the RX bond and generate a molecule of your inorganic acid as a byproduct. Now, before we discuss the mechanism of this reaction, we first need to take a look at some bond dissociation energy values. Now, these values will be important when we look at the mechanism. And so let's take a look at first all of the halogens. So if we have fluorine-fluorine bond, a chlorine-chlorine bond, bromine-bromine, and iodine-iodine, right? So the BDE, these are all in kcals per mole. These are going to be 38, 58, 46, and 36. For HX, the BDE for HF is 136, HCl is 103, HBr is 87.5, and for HI is 71. For the alkanes, if we have, let's say, methane, that BDE is 105. If we have ethane, that's 100.5. If we have the isopropyl version, that's 99. If we have the terp-butyl version, that's 95. And finally, the RX BDEs. Any alkyl chain, let's just pick one. Let's do a propyl version for chloride is 85. The isopropyl version for chloride is 85. And the terp-butyl version is 83. So the trends for the sigma CH bond strength should make sense for us when we consider the radical stability. So sigma donation, as you move down the column here, sigma donation increases. And so if you were to generate a terp-butyl radical, that's much more stable than a primary or methyl radical. Okay, so now that we have these bond dissociation energies, let's talk about the free radical halogenation reaction. Halogenation is also a chain reaction. And so the mechanism for the reaction of methane with Cl2 in the presence of light has the following steps. And so step 1 is an initiation event. Right, so this is a photochemical homolytic cleavage. So the chlorine-chlorine bond will break homolytically to generate two radicals in the presence of light. Step 2 is a propagation step. Right? This is actually an abstraction step. Right, so you have a chloride radical here. We're going to react it with methane, and so we're going to get this to react with one of these CH bonds. Chloride is going to grab the hydrogen atom. Electrons are going to move up onto that carbon atom as a new radical. Right, so plus we have CH3 dot. Okay, now let's write in some of our bond association energies. So the BDE for CH bond is 105 kcals per mole. The BDE for chloride HCl is 103. Now this is a +2 difference, but 2 kcals per mole is not a high enough energy barrier to prevent this reaction from occurring. And so the reaction continues. So we have step 3 now. Step 3 is another propagation step. This time it's an addition. So addition of this carbon-centered radical to generate a new carbon chlorine sigma bond. So we're going to take chlorine gas and we're going to halogenate that radical. And so we're going to end up with our new product, methyl chloride, plus a new chloride radical. So this is our product. The new chloride radical will then go back to the second propagation step. It will recycle. Let's take a look at our bond dissociation energies. So the chlorine-chlorine bond is 58. The carbon-chlorine bond is 84. That's really exothermic. And so this reaction proceeds really nicely. All right, so this is going to go around and around and around between steps 2 and 3 until you've consumed all of your methane and consumed all of your chlorine gas, and you now have these two, this product here, but you have a tiny little amount of radicals hanging around. So we need to terminate this reaction. So the termination step is, of course, a dimerization mechanism. And so let's say we have two chlorides coming together to give us chlorine. Or let's say we have two methyl radicals coming together to give us ethane. Doesn't matter which ones you choose. Remember, these are inconsequential because they happen in such low quantities, low concentrations, that it's not going to have an impact on your overall yield of the molecule, of the reaction. Right, so here's the overall reaction. You're taking methane, you're halogenating it with Cl2 in the presence of light. All right, so if you see that we add up all the bond enthalpies that are either formed or broken, the free radical chlorination is exothermic, right? And so if we were to take 84 minus 58, right? So that's minus 26. Here's plus 2. And so the net result is you got a minus 24 kcal per mole exothermic reaction. Okay. Free radical bromination operates by the same mechanism, but is much less exothermic since the first propagation step is highly endothermic, plus 17. And this will have consequences for selectivity when using more complicated alkenes. So what happens when methane is not the starting substrate? Well, that's simple. Since there are many types of hydrogen atoms to abstract in the first propagation step, mixtures will actually result. And so let's say we were to take this alkane and react it with chlorine in the presence of light. We're going to get a mixture of the monochlorinated product, right? Where you get the butyl chloride in the 1 position or the butyl chloride in the 2 position. Now, what would the ratio of the products look like? Well, this depends on the number of hydrogen atoms at each site, right? So we have 3 hydrogen atoms here and 3 hydrogen atoms here that could give us this product, whereas we have 2 hydrogen atoms there and 2 hydrogen atoms there that could give us this product. So for the primary carbon, there are 6 hydrogen atoms, but for the secondary carbon, there are 4. So we might expect statistically that the ratio between these two is 60 to 40 in favor of the 1-chlorobutane, right? Well, the experimental ratio is actually more like 28 to 72, right? So it's not 60 to 40. Now, why is this? The reason this is because the secondary radical is more stable. So when you're undergoing the propagation step, you're always going to undergo the propagation step so that you generate the more stable radical. So its hydrogen atom, the secondary position, its hydrogen atom is abstracted faster. The energy barrier to get to a secondary radical is much lower. So the rate of abstraction of a hydrogen atom at the secondary center is actually 3.9 times faster than a primary center. And actually a tertiary radical is even more stable than a secondary radical. It's going to form 5.2 times faster than a primary center. And so the selectivities are going to be very different than what you might expect statistically. And so let's draw out what the selectivities are. So for chlorine and light, the selectivities are 5.2 for a tertiary center, 3.9 for a secondary center, and 1.0 for a primary center. Okay, so if you have secondary, primary, and tertiary centers in your molecule, you will chlorinate those positions in those ratios. But look what happens with bromine and light. For bromine and light, it's much, much more selective. So these values tell us that bromination, free radical bromination, is much, much more selective than free radical chlorination. So usually, only the tertiary position is halogenated. Again, let's look at why this is the case through the BDE values, the bond dissociation energy values. The propagation step for bromination is endothermic, meaning it is more sensitive to the stability of the free radical intermediate. Another way of thinking about this is that the transition state is much more product-like. And so it's going to want to resemble more the radical intermediate. And so if it wants to resemble the radical intermediate, you want a way of stabilizing this radical intermediate. And so one way of looking at this is to say, all right, if I have this CH bond here versus this CH bond here, and I'm reacting it with chloride or bromide radicals, in the case of the chloride, right, I'm abstracting this hydrogen plus HCl. This bond dissociation energy is 103. This one is 100.5. In the case of bromide, this one is 87.5. Right, our delta H values here are going to be about minus 2.5 and plus 13. And so this bromination reaction is not really favored. And so what you'd rather do is to make this alkane itself much more highly substituted. And it's even further to state that this particular transition state looks like the product itself. So the product, the abstraction of this hydrogen is going to more look like the bonds are forming between hydrogen and bromine more closely than between carbon and hydrogen. So thus, what we can say from this is that the chlorination of alkanes is used primarily when all hydrogen atoms are equivalent. So if you want to do a chlorination when all hydrogen atoms are equivalent. Usually this occurs in symmetrical systems. If you want to do a bromination, use a bromination to prepare tertiary centers. Notice we don't use fluorine and we don't use iodine. Fluorine is explosive, or it's exothermic to a great extent, and iodine is too endothermic to have any appreciable rate. And so fluorine's too reactive, iodine is not reactive enough. Now one more reaction we have to worry about. The allylic free radical halogenation. So in an allylic halogenation, we're basically going to take advantage of the fact that we have an allyl system that is going to stabilize the resulting radical. And so what we can do is, let's say, take this allyl system, this alkene, and we're going to react it with NBS. If you recall, NBS has the following structure. Same reagent we had in addition reactions to alkene. We're going to heat it up in the presence of carbon tetrachloride as solvent. And what we get in this reaction is an allylic bromination. Now, there's an important point to consider here, is that in this cyclohexene molecule, there are actually 3 types of CH bonds where the hydrogen atoms could be abstracted. There's this vinyl CH. There's the allylic CH, let's say this one. Let me put them in different colors. There's this allylic CH, and then there's the alkyl CH, the methylene. Now, since abstraction of the allylic hydrogen would lead to the formation of a resonance-stabilized allylic radical, that CH bond is much weaker, and so the bond dissociation energy will be lower. And so the only reason why we can use much more mild conditions using NBS is because this bond dissociation energy is a lot weaker. And so what can happen is we can take NBS, we can break that bond homolytically in the presence of heat. That gives us a bromide radical plus a succinimide radical. right? There's our step 1, formation of those radicals, the initiation step. Step 2 is one of our propagation steps. That's the abstraction. And so we're going to take our NBS, our succinimide radical. It's going to abstract this CH that we have right here. Generates a allylic radical. So we have the succinimide as a byproduct plus the allylic radical, which can undergo resonance stabilization. Okay. Step 3 involves another propagation step where we take that radical and we react it with another molecule of the starting material, the NBS. And that's going to generate an addition to give us our product plus the succinimide radical again, which can shuttle back to step 2. It can recycle and repeat this over and over and over again until you have consumed all of your NBS and all of your cyclohexene, and then you have step 4 where you get a termination step, dimerization. So let's say we take, 2 of these molecules, they come together to generate a dimer. And then you have a complete mechanism. All right, so that's reactions of radicals.